Welcome back to World Decoder. Today we uncover the optical magic that allows modern technology to exist at the atomic scale. To create microchips with details smaller than a virus, ASML machines need optical components that defy the very laws of nature. While we marvel at the intricate chips powering our devices, the real hero is the unseen mirror system guiding the light. We are decoding Carl Zeiss, the German company behind the mirrors known as the flattest objects ever created in the universe. In older chip machines, standard glass lenses were sufficient to focus light. However, technology has advanced to a critical breaking point. With extreme ultraviolet light used by ASML, every known type of glass absorbs the energy, swallowing the light before it works. This means the light beam would be devoured by the lens before it could ever etch a pattern onto the chip. Zeiss engineers realized they had to abandon lenses entirely. They needed a radical new approach to handle this powerful light source. Their solution was the high numerical aperture mirror system. Instead of passing through, the light dances across a series of mirrors. This method ensures the energy is preserved, allowing the EUV light to focus directly onto the silicone wafer with extreme precision. But this is not just about reflection. It is about achieving a level of flatness that challenges the limits of physics. If the light deviates by even a fraction of a billionth of a millimeter, the entire chip production process becomes useless. To understand this precision, imagine magnifying a single Zeiss mirror until it is the size of the entire country of Germany. On this Germany-sized mirror, the highest mountain or bump on the surface would be less than 0.1 millimeters tall. This is a flatness so absolute that the human mind struggles to comprehend it. Without these massive, country-sized geographical comparisons, it is so flat that if you reflected a laser beam across thousands of kilometers, it would remain perfectly focused and straight. Your bathroom mirror is a rugged landscape of peaks and valleys compared to the perfection required for semiconductor manufacturing at this level. These mirrors are not simple slabs of glass or metal. They are constructed from hundreds of alternating layers of specific materials. They typically consist of about 100 ultra-thin layers of molybdenum and silicon, stacked with a precision that borders on insanity. Each layer is only a few nanometers thick. We are talking about engineering that takes place at the scale of individual atoms. If just one of these layers is off by the width of a few atoms, the multi-million-dollar mirror becomes expensive scrap. The margin for error is effectively zero. Perfection is not just a goal, it is the absolute baseline requirement for operation. For 30 years, optical giants from Japan and the United States have tried to chase this technology, but they all failed. Why is Zeiss the only survivor? Because the barriers to entry are built on decades of proprietary knowledge and specialized machinery. One secret weapon is their polishing technique. Zeiss uses ion beams to shave off individual atoms from the surface of the mirror. They sculpt the surface until it reaches the desired flatness, removing material atom by atom in a process of slow perfection. This process takes place in a vacuum, ensuring that not even a stray dust particle can interfere with the polishing work. Zeiss and ASML are not just partners, they are a single organism. ASML owns a significant stake in Zeiss to ensure loyalty. Together, they have built a fortress of knowledge that no other nation or company can replicate in a short amount of time. If ASML is the arm that draws the chip, then the Zeiss mirror system is the eye that makes vision possible. Without Zeiss, the billion-dollar ASML machines are nothing more than a very expensive pile of scrap metal and useless wires. This collaboration is the sole reason we are now approaching the era of 2-nanometer chips, pushing computing power to new heights. Every mirror undergoes months of testing. The quality control is so rigorous that many mirrors are rejected before leaving the factory. Transporting these mirrors is a mission in itself. They are moved in special containers that isolate them from all external vibrations. From Germany, they travel to chip fabricators in Taiwan and Korea, becoming the heart of the machines that run the world. Your smartphone, your laptop, and your car all depend on the flatness of these mirrors produced in a small German town. In Oberkochen, Germany, precision is a culture. Generations of families have worked at Zeiss, passing down the secrets of optical perfection. The legacy of Carl Zeiss lives on. What started as simple microscopy has evolved into the backbone of the digital age. It is a poetic irony that to see the smallest things in existence, we need mirrors flat enough to span countries. Controlling light at this level requires mastering quantum mechanics and material science simultaneously. It is the ultimate test of engineering. The mirrors must also withstand heat. The energy from EUV light is intense, but the mirrors must not warp or expand. Zeiss engineered complex cooling channels behind the reflective surface to dissipate heat instantly, maintaining that crucial atomic level flatness. While space telescopes look at the stars, Zeiss mirrors look at the silicon. Both require perfection, but Zeiss works on a nanometer scale. A single speck of dust on these mirrors would cast a shadow on the chip, ruining millions of transistors in an instant. Testing involves creating a vacuum environment that mimics deep space, ensuring the mirrors behave predictably under the harshest possible conditions. The data generated from measuring one mirror is enough to fill hard drives. Every micrometer is mapped, analyzed, and corrected. Billions of euros are poured into research and development annually. This is a game where only the deepest pockets can play. The final product is a masterpiece of human ingenuity. It is arguably the most precise object ever manufactured by human hands. Chip manufacturers wait in line for years to get these systems. The supply is limited by the sheer difficulty of production. This technology is a strategic asset. It is guarded closely, preventing other nations from easily replicating the semiconductor supply chain. As we move toward artificial intelligence and autonomous systems, the demand for more powerful chips and better mirrors will only increase. Zeiss is already working on the next generation. High-end AEUV mirrors will be larger, flatter, and even more complex to build. They are constantly pushing the boundaries of what is physically possible, turning science fiction concepts into industrial reality every single day. So the next time you look in a mirror, remember that somewhere in Germany, a mirror exists that makes your mirror look like a mountain range. From raw materials to the most expensive glass on Earth, the journey of a Zeiss mirror is a triumph of persistence. It proves that when humans collaborate with precision and patience, we can overcome obstacles that seem insurmountable to the naked eye. The machine closes, the vacuum engages, and the light begins to dance across the mirrors. The future is being printed now. This invisible dance of light and mirrors connects us all, powering the digital infrastructure of modern civilization across the globe. We have conquered the nanometer, but what lies beyond? As Zeiss continues to polish, we will surely find out soon enough. Nature creates beauty in chaos, but Zeiss creates beauty in absolute order. It is a different kind of perfection, cold but magnificent. Layer by layer, atom by atom, the structure rises. It is a testament to the incredible patience required for true innovation. Measurement is just as important as manufacturing. You cannot build what you cannot measure, and Zeiss measures better than anyone else. These mirrors give machines the ability to see and create the digital world. They are the corneas of the artificial intelligence age. Imagine a world without them. No smartphones, no modern cars, no internet. We would be thrown back decades in time instantly. The partnership between Zeiss and ASML is a modern industrial miracle, a monopoly built on pure, unadulterated engineering excellence. They transform physical light into digital data. It is a magical conversion that happens billions of times every single second. From the inside of the machine, the world looks different. It is a world of extreme violence controlled by extreme calm. The light source is created by exploding molten tin. The mirrors must tame this violent energy and direct it with grace. It is a study in contrasts, the explosive power of plasma generation versus the silent, static perfection of the reflecting mirrors. Knowledge is passed down like a torch. The secrets of making these mirrors are not written in books, but learned through practice. Carl Zeiss started this journey over a century ago. He could never have imagined his company would one day print the future. From helping biologists see cells, to helping humanity build artificial brains, the mission remains the same, seeing the invisible. While a prism splits light, a Zeiss mirror disciplines it. It forces the chaotic photons to march in a perfect, orderly line. The cities we build on silicon are more complex than any city we have built on Earth, thanks to these mirrors. Behind the cold metal and the vacuum chambers, there is human intent, the desire to improve, to shrink, and to accelerate. The road ahead is not easy. Physics fights back harder with every nanometer we shrink, but Zeiss seems ready for the fight. In the grand scheme of things, these mirrors are small, but their impact reflects across every aspect of our modern lives. ASML provides the canvas, but Zeiss provides the brush. Together, they are painting a masterpiece that is changing human history forever. If you enjoyed this deep dive into the world of extreme engineering, please like this video and share it with fellow tech enthusiasts. We have many more stories about the hidden technology shaping our world. Check out our channel for more episodes like this one. The mirror reflects not just light, but our potential. It shows us that perfection is possible if we are willing to work for it. This has been World Decoder, exploring the limits of physics and engineering. Thank you for joining us on this journey today. Subscribe to see what we decode next. Until then, keep looking closer at the world around you. Goodbye.